Alright, so today we're looking at lesson 52. We're looking at plane mirrors and concave parabolic mirrors. So hopefully you'll understand how to deal with plane mirrors and concave parabolic mirrors after this lesson. We're going to start off with plane mirrors. What we see with our eyes is determined solely by the light rays that enter into our eyes. So everything that we see is determined by the light rays that enter our eyes. We see the rays that are reflected because these are the rays that enter our eyes. All of the rays that are reflected from an object are the ones that are going to go into our eyes. The rays enter our eyes from every point on the object. So if you look at this little arrow, we've got an eye and we've got rays that are reflected from the top and from the middle and from the bottom. And those are the ones that are going to enter our eye. Now there are going to be rays that are reflected over on this side or in the bottom. But those, if you keep going, are not ever going to enter our eye. Those are going to be away from our eye. And so those are the ones that we won't see because they don't reflect back to our eyes. In our discussion of visual images, we're going to consider only the ray from the top of the object. So we have to remember that this ray is exactly like the myriad rays that enter the eye from all points on the object, but we are going to only consider the ray from the top of the object. Whenever you have light strike a boundary between two optical media, some of the light is refracted, some of it is absorbed, and some of it is reflected. So anytime you have light striking a boundary, you can have some that's refracted, some absorbed, and some reflected. A boundary or a surface that reflects almost all of the light that it strikes it, such as like a hubcap, is called a mirror. So if it reflects almost everything, that's going to be called a mirror. So that'd be something that you shine a flashlight at and you get blinded almost because you've got so much light coming back at you. It'd be almost like just taking the flashlight and shining it directly into your eye. Those are going to be called mirrors. We only consider ideal mirrors, and so those are mirrors that are perfectly smooth and reflect all of the light rays that strike them. Now in real life, we may not have ideal mirrors. We may have mirrors that reflect most of the light rays that strike them, but we are only going to consider ideal ones that reflect every bit of the light that hits them. And then they're also going to be perfectly smooth. Mirrors made of glass that are coated with mercury are good approximations of ideal mirrors. So those are examples of, or that is an example of an ideal mirror. And we say that a flat mirror is called a plane mirror. So if it's completely flat, it's a plane mirror. Most of you probably have a plane mirror in your bathroom. You look at it, well, some of you look at it more than others in the morning when you're getting ready. That's called a plane mirror. I'm sure some of you never look at the mirror at all. You don't care. You just wake up and come to school. But there are some of you in here that look at a plane mirror every morning. We call the reflecting side of a mirror the light side of the mirror, and we call the other side the dark side of the mirror. So the side that you are looking at is called the light side. The light hits it and reflects back to you. And then the other side of the mirror is the dark side. You don't see it. Think about the dark side of the moon. I'm not sure if any of y'all have heard that term, but the side of the moon that we see, the opposite side of it is called the dark side because the sun hits the moon and reflects it to us, and then the other side isn't getting the sunlight, and so it's called the dark side. We don't see it. It's on the other side. That's why it's called the dark side. So the image distance is going to equal the object distance whenever we have reflection. And so this is our mirror here. And so this is our object and this is our image. The distance here and the distance here are going to be the same. And likewise, the height of the image, this height here and this height here, are going to be the same. And that's true if you're looking up to your image and your object, or if you're looking down. The distance between the mirror and the image in your object are going to always be the same, and the height of the image and the object are going to be the same. The position of the image behind the mirror is fixed. Images that appear to be located in the mirror or behind the mirror or on the dark side of the mirror are called virtual images. And so I'm going to draw a little picture here. We've got a person, and they're getting ready. They're brushing their hair in the morning. There's their lovely hair. Here is our mirror. And then we've got a person in the mirror. And they're brushing their hair because they are doing the mirror image of whatever this actual person is doing. This one here is an image that is behind the mirror, or it's in the mirror, or on the dark side of the mirror. It's a virtual image. It's not real. It's just reflected from this actual person right here. And so this position of this person, this virtual person, is fixed. It's not going to change. The image is not upside down, but it is going to be upright. So your image isn't upside down, it's upright. Every image on the dark side of any mirror is called a virtual image, and it's always going to be upright. So anything that's on the dark side of the mirror is going to be upright. Thus the words dark side, upright, and virtual always go together. Dark side, upright, virtual, they always go together. If you've got an image that's on the dark side of the mirror, it's going to be upright and is a virtual image. So now we're going to look at concave parabolic mirrors. So it tells in the figure in the center and on the right, we show cross sections of a three-dimensional curved mirror that has the shape of a paraboloid of revolution. So this word right here, you say it paraboloid. So cross sections have the shape of a parabola, and the mirror is called a parabolic mirror. So they've got an example. You've got three mirrors, and as you make them more curved, that's going to be a parabolic mirror. Parabolic mirrors are very expensive to manufacture, and for many applications, a spherical mirror is going to be an adequate substitute, especially if the portion of the mirror used is restricted to the region that's near the principal axis of the mirror. So most of the time, you're actually going to have a spherical mirror, not a parabolic mirror, because they're so expensive to manufacture. So the focal length of a spherical mirror is half the radius of the curvature of the mirror. And that is something that you are going to need to work these problems. You can write that on your note card if you would like. The focal length of a spherical mirror is half the radius of the curvature of the mirror. Okay? I'm going to go back to pre-cal when we talked about parabolas. There's this point here that's called the focus. And the length from here to the vertex, this segment is called the focal length. Whoops, there should not be two C's there. So that's the focal length. And so whatever this length is, it's going to be half of the radius of the curvature of the mirror. Okay? So let's look at an example. We've got an object 1 centimeter tall. Is placed upright on the axis of a concave spherical mirror at a distance of 5 centimeters from the mirror. The radius of the curvature of the mirror is 6 centimeters. Use ray tracing to find the location, orientation, and height of the image, and also find the magnification. So I started by going ahead and drawing the picture that they gave us in the book, or putting it in here for us. Normally, you're going to have to draw this figure out. So we start off by making our curve for our mirror. Then we have our principal axis here. And so we put our F, that's our focus. We don't know exactly where it is yet. We put our C for the center of the sphere. And then we know that we have an object that is 1 centimeter tall. And it's on the axis here. And the object is 5 centimeters from the mirror. So this distance here is 5. And so if you look, you've got 2 and 3, total of 5. Then they told us the radius of the mirror is 6. So that means that one more unit, 1 more centimeter past the object is the center of our mirror. And so then, if we know that the radius is 6, going back, the focal length of the mirror is half of the radius. So if the radius is 6, that means that the focal length has to be 3. So this part here would be 3. Okay? And then that leaves this to be 2 since this part up here was 5 centimeters. Okay? So we draw this as our object. So we're looking for the location, orientation, and height of the image. And then we want to find the magnification. All right, so we're going to have to use this picture. So you should go ahead and draw it on your paper so that we can figure out the location, orientation, and height, and the magnification. This, you can actually just do a straight line. You don't have to do a curve unless you just want to. So the first thing that you do is to draw 2 rays from the top of the object. So the first one we're going to do parallel to the axis. And so you keep going until it hits the mirror. And then when it reflects down through the focus this direction. Well, it should go through the focus. It should go about like that. Okay, so that's the first one. It goes from the top to the mirror and down through the focus. And then the second one, you draw through the focus until it hits the mirror. It hits the mirror and then it goes parallel to the axis. And you keep going until it intersects with that other line that you had just drawn. So it goes through the focus, hits the mirror, and is parallel to the axis. So those are the 2 that you draw. And the intersection of the 2 reflected rays, this point right here, represents the top of the image. So this is going to be the height of our image. And the image is a real image. It's located in front of the mirror. And it is also inverted. Instead of going up, it's going to be going down. So all real images are inverted images. So if it's a real image, it is inverted. So real also means inverted, and inverted also means real. For any mirror, light side, real, and inverted are going to go together. Okay, so light side, real, and inverted all go together. And so we can measure and we can figure out that the height of the image is approximately 1.5 centimeters. So this height here is approximately 1.5 centimeters. So I'm going to do it in green, and I didn't actually get the point exactly where it needs to go. It should go right here. I didn't draw it exactly accurate. But we've got this triangle here. And then we have this triangle here. And so we're going to set up a ratio of the legs. So the height is 1. And the height of this triangle is h. That's what we're looking for. And then the other leg of this top triangle is 2. And then the bigger triangle, the leg is 3. So we'd have 2 over 3. So cross multiply, you get 2h equals 3. And so your height is 3 over 2, which is 1.5 centimeters. So that's the height. The location is in front of the mirror. And it's inverted. And then we want to find the magnification. So to find the magnification, you do the height of the image divided by the height of the object. So the height of our image is 1.5. That's what we just found. And the height of the object is 1.0. That's what they gave us here. So if you divide that, you get 1.5. And so that would be your magnification. So magnification, to find that, you do the height of the image over the height of the object. Okay. Looking at the next example, we have a 1 centimeter tall object placed upright on the axis of a concave spherical mirror at a distance of 1 centimeter from the mirror. The radius of curvature of the mirror is 6 centimeters. Use ray tracing to find the location, orientation, and height of the image, and also find the magnification. This is our sitter. It's 6 away from the mirror, and this time they just did a straight line. That's fine to do a straight line. You don't have to do a little curve. So this distance here is 6. This is our focus. It's halfway between the two. So this length should be 3. Half of 6 is 3. And then we have a 1 centimeter object placed upright, a distance of 1 from the mirror. So we are going to do 2 rays from our object. First one is parallel to the axis, and then it comes back and goes through the focus. Okay, so that's the first one. And then the other one is going to go through the focus and then parallel to the axis. And so if we went this way, we would never actually hit the mirror. So we go through the focus, we come up this way. I'm going to do a little dotted line, come up this way to the top of the object. And so then we keep going and we hit the mirror and we go parallel. And so this one's a little bit different than the last one because, as you notice, these two lines only intersect here at the top. They don't actually intersect. And so what we have to do, we have to move this over a little bit. We're going to have to extend our 2 rays. So we're going to take this one and it's just going to keep going this way. And then this one is going to keep going up this way. And so they intersect right here. So this is our axis. And this is our new object. Our virtual image, because it's on the dark side of the mirror. And so it is upright. So the location is in the mirror or on the dark side of the mirror. It's upright, and then we've got to find the height of the mirror. The height of the image. So to find the height, alright, so we have 2 triangles. I'm going to draw them in blue. We've got one right here. That's a terrible triangle, sorry. We got that triangle there, and then I'm going to draw the other one in red. We've got this triangle right here, and those are similar triangles. And so I'm going to redraw the blue one over here. The height of it is 1, and the bottom leg is 2. And then for the red one, we know that the bottom is 3. And so if you set up a ratio, you'll end up getting that the height here is 1.5. I'm sorry, this red one should be more up here. Like that. It should be sharing this part of the hypotenuse. And so this height here is 1.5 using ratios. And so if you come across, this height of the image is also going to be 1.5. And then to find the magnification, you do the height of the image, which is 1.5, over the height of the object, which is 1.0. And so our magnification would be 1.5. Okay, so that's your magnification. So that's how those work. You do definitely have to draw the picture based off of the information that they give you in order to make it work, to be able to figure these out. The more you practice with them, the easier they do get, but these do take a little bit of practice. The book does say if you have a concave mirror, your virtual images are always larger than the object. And if you look here, our virtual image was larger. It was about 1/2 centimeter bigger, or 1.5 times bigger than the object that we started with. Okay, so your homework is 1 through 20, and then 1 through 5 for the curveball questions. So make sure that you do those tonight so we can go over any questions you have tomorrow.